Hi everybody. Today I get to show you a really nice exercise. We're going to find the area of a triangle, coordinate geometry. We're going to graph this triangle ABC, show its altitude and its length of its base, multiply and come up with the area. It's really a great question. The area of a triangle doesn't sound so interesting perhaps, but the way we get to work this one really gives us a chance to practice some of the things we've been thinking about all along. I worked it just a little while ago, and then I realized there are some skills that you got to have going in to do this workout well. So let me show you a couple of things. One thing you want to be able to do is to reduce a radical. What do you mean reduce a radical? Like if we were working with something that said the square root of 36, I hope you wouldn't leave that the square root of 36. You'd write it what it's equal to, because the square root of 36 is just equal to 6. And we would simplify that radical, wouldn't leave it in that situation. But here, thinking that same idea, we're going to try to reduce these radicals. And the name of the game is to find perfect squares that are factors here. And what do you mean by perfect squares, mister? Well, like 1 squared is just 1, and 2 squared is 4, 3 squared is 9. Let's march up to like 12 squared. 4 squared we got 16. 5 squared we'll have 25. You get ahead of me. Let's just get those perfect squares somewhere so we can keep them handy and be thinking about them. So we got 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 121, and 12 squared, 144. And we could go on and on with 169 and so on, but 190. But let's stop. We've got some perfect squares here that'll probably be sufficient for what we'll have to do with this little exercise. The thought is, are any of these perfect squares factors of this number in that radical? And if they are, then we'll be able to reduce this radical. Now you might be saying, well, that's 9 times 8. And in fact, it is 9 times 8. And that would be okay. We could work it that way. If you thought, well, it's 9 times 8, and I know the square root of 9, that would come out of the radical. It would become a 3, because the square root of 9 is just 3. And we would still have 8 within that radical, wouldn't we? And if I look at that for a second, 3 with the square root of 8, but that square root of 8 is really, that's 4 times 2. And I know the square root of 4 is just 2. So that 4 comes out of the radical, becomes a 2, multiplies with that 3, gives me 6. And I do not know the square root of 2. I got to leave it inside that radical. Square roots of 2. There's a better way we could have done that one. I hope you saw it. Is there a bigger perfect square that goes into 72? And in fact there is. That could have been 36 times 2. 36 is a perfect square, and it's a factor of 72, fairly obvious one. And I know the square root of 36, it's just going to be 6. So we call that 6 root 2, or 6 times the square root of 2. We found it the other way, but it's just kind of harder when you took out smaller perfect squares. So how about the square root of 75? Can that be written in a more concise way? Is there a perfect square that's a factor? I say there is. That's 25 is a factor of 75, so this must be 25 times 3. Now, we don't know the square root of 3. It's about 1.732, but that's not what we care about. We're going to leave that the square root of 3 because we only have a decimal approximation. But we do know the square root of 25. It comes dancing out of the radical, becomes a 5, because the square root of 25 is 5. And we do not know the square root of 3 except for an approximation. We'll leave it 5 root 3. 5 times the square root of 3 is the best form for this value. What perfect square goes into 128? You might be thinking, well, it's 4 times 32, but I'd say bigger than that. It's 64 times 2, isn't it? Yeah, I think it is. 64 times 2. Let's write it that way. Find the biggest perfect square you could that's a factor of the number in the radical. I think it's called the radicand. Anyway, that's 64 times 2. I know the square root of 64. This number and this number are the same, and I know the square root of 64. It becomes 8. I do not know the square root of 2, about 1.414, but we don't want a decimal approximation. Let's leave it 8 root 2. This value, hit it with a calculator, and that one are exactly the same. They are the same thing, but this is a much better value to work in our problem, and to work in lots of problems. You want that reduced radical form. We'll be seeing it throughout the year. Well, how about the square root of 288? 4 goes into it, but maybe something goes into it bigger than that. Yeah, 144, huh? So, if you see the bigger radical, it makes it easier to go. You certainly could divide it by 4 and then divide it again, because 4 times 72 is that, and 72 is 9 times 8. So you could work it out eventually. But if you saw that it was 144 times 2, you'd get there a lot quicker. Hey, I know the square root of 144. It's 12. So here we have 12 times the square root of 2. And we could get close if we needed an approximation, but I'm saying for what we're doing right now, let's keep it perfect. Let's keep it exactly that, 12 square roots of 2. Now what about that square root of 80? Just learning about how to reduce a radical. Any perfect squares go into 80? It's 4 times 20. And that's true, you could work it that way. Let me show you what I mean about that. When you call that 4 times 20, you could have said, well, I know the square root of 4. It's a 2. I got to work on that square root of 20 because we do not know the square root of 20. But you're thinking, well, keeping that 2 on the outside, that 20 could be written as 4 times 5. And I know the square root of 4. So that 4 comes out, becomes a 2, multiplies with that 2, and it gives me 4. I do not know the square root of 5 except an approximation. Let's leave it inside the radical. So that becomes 4 square roots of 5. But some people in this crowd were probably thinking, hey, that 80, wasn't that really just 16 times 5? Yeah, 16 times 5 is 80, and I know the square root of 16 going to be 4 root 5. And so, to do this well, you can work it, but it's just harder if you don't know those factors. So you have to add and subtract, multiply and divide. Well, it pays off here. Let's keep going. We've got one more to do. Square root of 242. And if you didn't see anything with it, you could divide it by 2 and see what happens. Divide this by 2, see what happens. Divide by 4, see what you can find. But 242, yeah, that's 121 times 2, isn't it? 121 times 2, and 121 is one of those numbers we care about. That's 11 squared. So this is 2 times 11 times 11. We know the square root of 121 is 11. We do not know the square root of 2, except for an approximation. We'll leave it 11 root 2. 11 times the square root of 2, better said. Now, that's important, and we'll use that to do some of the things in a minute. Other question might come up, how do you multiply with radicals? And it's really nice, and it's a simple rule. Let's look at this. A number with a radical part, multiplying with another number, a number outside and a number within the radical. If you were to multiply those, it works as you wish it would. The outside number multiplies with the outside number, and the inside part multiplies with the inside part. To show what I mean by that, let's multiply a few right here. And you would multiply the outside part, which would give us 6. And the inside part with the inside part, which would give us 18. And that's how you multiply with radicals. But look what this will allow me to do. This 6 square roots of 18. I hope I know what you're thinking. That 18, why, that's 9 times 2, isn't it? And since I know the square root of 9 is 3, I can pull that 9 out of the radical. It becomes a 3. Multiply with that 16. That would multiply with that 6. Gives me 18. I do not know the square root of 2. It stays within the radical. So I'm saying to you that this product is equal to 18 times the square root of 2. How about that? Let's do another one. And so it's a simple rule. The outside guy with the outside guy, and the inside guy multiplies with the inside guy. So here that looks like 20 square roots of 14. Now, can we do some special work on that radical? I say, no, 14, just 7 times 2, and I don't know the square root of 7, I don't know the square root of 2, I just got to leave it like that. But let's see what we can do here with this next case. You get ahead of me. This is a nice one. It works. There's lots of things will work. 3 times 5 is going to give us 15, that's easy. And then the square root of 3 times the square root of 3 gives me the square root of 3 squared. That's really 9, though. And hey, I know the square root of 9. The square root of 9 is just 3. I multiply it with that 15, and yep, I got 45. So this answer is cleanly at 45. Let me leave this little box around it too. Maybe that one also. So that isn't that interesting? It could work out that way. And what's going on here? When you have the same radical in here, there they show the same radical. Here we're going to say the same radical. And it's going to work out cleanly as well. Let's take a look. Outside guy with outside guy is going to give us 42. Square roots of, and 2 times 2 is just going to give us 4 within the radical. But lo and behold, we know the square root of 4 to be 2. So 2 times 42 is going to give us 84. And that is the product of 7 root 2 and 6 root 2. It's worth 84. Now let's play a little bit longer. 9 square roots of 15 times 3 square roots of 6. Outside guy with outside guy. 27 square root of 6 times 15 is 90. Now there's probably something we could do with that 90, you figure? Yeah, I think so too. Blasting out at me, that's 9 times 10. So this should be written as this 27 times the square root of 9 times 10. I'm thinking, well, that 9, I know the square root of 9 that's 3 squared, so the square root of 9 is just 3. That 3 becomes out of the radical, multiplies with the 27, gives me 81. The 9 came out, the 10's still in there. Square roots of 10. And I'm here to tell you, this is a true fact, that if you were to multiply 9 square roots of 15 times 3 square roots of 6, you're going to get 81 square roots of 10. Isn't that a beautiful thing? One more time with feeling. Let's multiply these two. 16 root 49. Hey, I know the square root of 49. So this is going to be 16 times 7. Let's see, that'd be 70 and 42, so 112 probably? That's what I think that one ought to be, 112. Now, one more thing you got to know before we find around finding the area of these triangles. We got to know, how is it you find the area of a triangle? And I'm going to tell you, is that formula that you probably saw since you're in 5th or 6th grade. The area of a triangle is 1/2 times the base times the height. And I have some nice little scenarios right here, pretty easy. I'm just going to find the area of a couple of triangles. So here's this triangle ABC. We care for its area. And we're going to call this guy's base. And this is an obtuse triangle. It's got an obtuse angle right there. And actually the height of that triangle, or its altitude right there, is outside of the shaded triangle. I'm looking for the area of the shaded zone right there, that triangle ABC. But its altitude stands here. And we won't argue about that right for now, but I'm just going to go right to work with the formula. 1/2 times its base times its height. So that would be, in this case, 1/2 times, hey, that base, that's 7 times the square root of 5, isn't it? Put that in parentheses so we can talk about it if we need to. And the height, well, that's 3 times the square root of 5. Now, we have to think how we're going to work this product. I am a left to right kind of guy, and I think that's a good way to go, but I don't want to take 1/2 of 7 square roots of 5. Let's just keep the 1/2 on the outside for now. And multiply these other fellas. I'll put them in that bracket, whatever that product would be. And here we are multiplying some numbers with some radicals. And the outside guy with the outside guys are going to give me a 21 square roots of, and 5 times 5 is 25. So maybe you're doing this quicker than me, but I'm going to get it done. I got to think about what I really got here. That's going to be 1/2 times 21 times, and the square root of 25 is just 5. So I've cleaned up the multiplication with the radicals. I should multiply this out. I just have 1/2 of, and here we have 105, yeah? 21 times 5, 105. And if I'm looking for the area of that triangle, I'm going to have to call it, area of the triangle is 105 over 2. Because it was 1/2 times the base times the height. I never did work that 1/2 yet, did I? 1/2 of 105. Going to be 52.5, I guess? Yep, something about like that. Area of the triangle, 52.5. All right, let's play a little bit longer. We got another triangle to work with right here. We're going to find the area of this triangle PQR. And we got its base and we got its height. Let's roll. It'll be quick and easy. Area of the triangle ought to be 1/2 times its base, 4 root 7, times its height, 3 root 7. Now, last time I wanted to multiply the radicals first, but I'm thinking, hey, could you multiply 1/2 times 4 root 7? And yeah, you could. That would not be a problem. So 1/2 of 4 root 7 just going to be 2 root 7 times 3 root 7. And we're just going to multiply the outside guy with the outside guy. That'd give me 6 square roots of, and 7 times 7 is going to be 49. And we know the square root of 49. So we're going to have 6 times 7, the square root of 49 being 7. So if we have 6 times 7, yep, that's going to be 42. So I say the area of triangle PQR, in this case, would have been 42. I should have said something like that up here too. Yeah, I guess I did. Area of triangle ABC was 52.5. Now, I think you know everything you need to know to get ready to do this exercise. Let's go to the printed page I gave you and find the area of this triangle. I'm going to go ahead and pause and show that triangle. You should too. So I got triangle ABC showing over 8 and up 5 for A, over 0 and up 1 for B, and over 9 and down 2 to get to point C. Looks about like that. You should too. We're going to investigate this triangle. We're going to find the area of this triangle when we're finished. We'll know how many square units it holds, and I'm going to remind you just for a second. That's a square unit right there, probably as close as I could draw it. How many of those will fit in this triangle right here? We're going to know that in a minute. But here we go, to go through that process to find the area of triangle ABC. We're going to call segment BC the base of this triangle. And we're going to find the equation of that line BC. The first thing anybody needs when they're ever going to find an equation of a line is the slope. So let's go with delta y over delta x. And we're going from B to C, which was at 0, 1, that's point B. And C is at 9, -2. I'm going to hit it with a slope formula. I've got to know the slope of line BC. I expect it to be negative, wouldn't you? And would you expect it to be a big number or a small number? I mean, how much does it seem like it's going down and over? Not that fast. So a small fraction, and it ought to be negative, huh? But let's see about that right now. Give me a y-coordinate on top, 1 minus the other y-coordinate, -2, over, start with that 1, I've got to start with that 0, minus 9. 1 minus -2, that's really 1 plus 2, that's 3. 0 minus 9 is a -9. Let's reduce that fraction. Now that's a -1/3. So I got to ask myself, does this look like it's going down 1 and over 3? And I'm saying, yeah, my graph isn't perfect, but it's pretty close. I think we got the slope right. Find the equation of the line through point A. Oh, I have not found the equation of line BC. I just found its slope, huh? Let me get back to work right here. But I do have an act for doing just that. I'm going to choose either point B or point C. Let me choose point C for an interesting reason at 9, -2. And use this slope. I'll find the equation of the line that goes through point C. It also goes through point B. We're going through B and C that has this slope. I'll use that formula that we know and love. Y minus y sub 1 equals m times x minus x sub 1. Maybe we won't write that formula next time. We'll just know it. Y minus -2. I'm going to call that y plus 2. Equals m, and we got to use that slope of -1/3 times x minus the x coordinate of the point we've chosen to go through, and that was 9. So I have y plus 2 equals -1/3 x. As I multiply into the parentheses, here I have a negative times a negative. That's going to be a positive, and 1/3 of 9 is just 3. So I have a +3 right there. Now, we got to isolate this y guy on the left-hand side, so we're going to subtract 2 from both sides. Get y by itself. Y will equal -1/3 x plus 1. And I'm satisfied that is the equation of that line, BC. It would have been easier had we chosen this other point when you say, well, if you might have thought ahead of time that we know the slope had to be -1/3, and we know it goes to the point 0, 1, since 0, 1 is the y-intercept, somebody might have thought y equals mx plus b. I can just substitute right there and get that equation, and it would have been y equals, hey, what are we using for slope? Yep, that would have been -1/3 times x plus the y-intercept, and the y-intercept is 1. So you could have got the equation that way, I grant you, but I wanted you to do it this way. We do get the same answer, don't we? That's the equation of line BC. Now, find the equation of the line through point A. Got to go through point A. We're about to find the altitude, which is perpendicular to line BC. Find the equation of the line through point A. We're going to use this point. A has coordinates 8, 5. We just keep track of stuff like that. We want to go through point A with a line that's perpendicular to BC. And we know the slope of BC. A line that would be parallel to BC would have been -1/3. But if we want our altitude, it's going to go this way. Sorry about that. got to go this way. To be perpendicular to BC, we have to have a slope of a perpendicular line. That would be the negative reciprocal of negative 1/3. That'd have to be 3 over 1, wouldn't it? So now, what do we really want? We want the equation of the line through point A, that's here, that has this slope. I'm going to go for it right now. That'd be y minus 5 equals 3 times x minus 8. You may say, well, where did that come from? And I'll show you where that came from, and I hope you knew already. Y minus y sub 1 equals m times x minus x sub 1. I just made those substitutions. The y-coordinate was 5, the slope was 3, the x-coordinate was 8. Well, pretty soon you don't got to write that formula every time. You can just blow through it. Anyway, we got y minus 5 is equal to 3x minus 24. Let's add 5 to both sides of that equation so we can get y by itself. And that'd be y equals 3x minus 19. Yeah, I added 5 to that negative 24. I got negative 19. Now, that's a pretty crazy y-intercept. Is that valid? Could that possibly happen? Let's take a look at that. It might be kind of messy, but I think I should take a look at it. We're trying to go from point A to line BC perpendicularly. Now, I just happen to have this tool that should help me do that reasonably well. Let me see if I can't line it up correctly, because that should be a right angle right about there, huh? Just get it in a pretty good position. Something like that. And I'm going to bring it further down. Just get a look at that altitude. Bringing on that line down here. And I wonder, is it possible? Do you think the y-intercept of this thing could have been a negative 19? I'm thinking my graph isn't perfect. It looks pretty close. I think it could have been negative 19. I think what we're going to go with is, that's the equation of this line. Y equals 3x plus a negative 19, or minus 19. Now, comes to a really good question. Don't know that I've spoken enough to you about this, but here we go. We're going to find the coordinates of point Z. This is going to be point Z right there. The point where the line of base BC intersects the line of altitude from A. That point of intersection right there. Now, bear in mind, we have the equation of line BC. There it is. We have the relationship between x and y. We also have the equation of line AZ from A through that point Z. We know the relationship between x and y there. What might we do with these two equations to find the place where they intersect one another? Now, we can study that graph and try to figure it out that way, but I'm telling you, we've got to show that algebra. And the way to do it, and it's a beautiful algebraic way, set these equal to one another. That is to say, let me say that 3x minus 19 is equal to negative 1/3 x plus 1. We're trying to find the point, the single point in this plane that satisfies both of these two equations. And I'm thinking, well, if y equals this and y equals that, they got to equal each other. They both want the same y coordinates, and when these equal each other, we're going to find that x value this way. Now, that's why it works that way. You think that through yourself. But now, what do we got to do to solve this? Shouldn't we collect like terms? Let's get the x's in the same place. So I have this negative 1/3 x on this side. We should add 1/3 x to both sides. And when I do, adding 1/3 x to both sides, I have 3 and 1/3 x. Minus 19 for now equals 1. I got to get that 3 1/3 x alone so I can deal with that coefficient. So what I need to do now is add 19 to both sides. And when I do, I'm going to be left with 3 and 1/3 x on the left. Adding 19 to both sides equals 20. Now, many of you, I hope, can just see how many 3 1/3s there'd be in 20. That just comes to you. But most of us got to do a little bit of arithmetic here. So let me write this again. I'm going to rewrite it, but with an improper fraction for 3 1/3. And you remember how we find that? Is 3 times 3 is 9 plus 1. Plus that 1 right there gives me 10 over 3. X is equal to 20. All I've done just then is rewritten this. And I've replaced 3 1/3 with 10 over 3 because those are equal. And this is such an easy way to work with it. This coefficient on x, we can eliminate that coefficient by multiplying both sides by the reciprocal. Let's multiply by 3 over 10. And I should multiply the other side also by 3 over 10. Why? What did you do this for? What will it yield for us? Well, here I got 3 over 10 is 30, and 10 over times 3 is 30. 30 over 30 is equal to 1, so I got 1x right there, which is what we wanted. And on the right-hand side, what have we got? Well, I got 20 times 3. That 20 is over 1. 20 times 3, that's going to be about 60. And 1 times 10 is just 10, so I just got 6 right there. So I'm saying the x-coordinate is 6. That x-coordinate right there from point Z should be 6. That's what this is telling me. 6 comma something. That's how far over that point should have been. That's what this algebra tells me. Now we got to find that y-coordinate. And the truth is, I can take that x value of 6 and put it into this equation, and I'll get that y value. I can put it in the other equation, and it'll do the same thing. My space is a little bit crowded, but let me do at least one of those. Probably both of them, huh? You don't got to do both, but let's take a look. Y equals negative 1/3, just using this equation. Negative 1/3 x, I'm going to leave a blank for x there, plus 1. And what do we let x be this time? We'll let x be 6. Okay, so I'm going to let a 6 show right there. And I have negative 1/3 of 6. A third of 6 is 2, and a negative 1/3 of 6 would be a negative 2, plus 1. And that gives me the y value to be a negative 2 plus 1 and negative 1. So that makes me think that coordinate had to be at 6 comma negative 1. You might be saying, hey, mister, what if you would have done it with that other equation? I said it would have worked out just the same way, but let's take that little walk and see. Y equals 3x minus 19. And you were letting x equal 6 in both of these times to see that we get the same y value for that value of 6 for x. So using this equation, we work here, going to let x be 6. Yeah, that gives me y equals 18 minus 19, and that's y equals negative 1, huh? So we got that coordinate, which is what we needed so far. Now, still we got a couple of things to figure out. Use the distance formula to find the length of segment BC and AZ. A beautiful thing happens here. We're going to find the length of BC using the distance formula, and we're going to find the length of AZ. Both of these values, both of these lengths will have a square root, but the radical will be the same. It's all about the slopes of these lines. Since they have these negative reciprocal slopes, the rise and run, the hypotenuse, and the length are all going to be, by virtue of those slopes, the same radical. I'll show you what I mean by that. It's really kind of a beautiful thing. Let's get the length of BC. That's one of the things I got to do. I got to use the distance formula to get the length of BC and AZ. I don't want to screw this up. I'm going to take the coordinates of B, which is at 0, 1. And the coordinates of Z, we just, oh, that's BC, excuse me. And C was at 9, negative 2. And I'm going to hit it with the distance formula, which looks like this. A couple of parentheses with some exponents. And let's just fill in those x coordinates here, those y coordinates there. The difference in the x's, so that'd be 0 minus 9. And here we'd have 1 minus negative 2. Keep those skills sharp. We'll need these. Here we got negative 9 squared, huh? Plus, and 1 minus a negative 2, that's a positive 3. 2 minus signs on the same number. Let's square them up and see what we get. That's a positive 81. Yeah, any negative number squared, it goes positive. And 3 squared gives me 9, so I have here the square root of 90. You might be saying to yourself, hey, I think I can reduce that radical. Let's reduce that radical. You know any perfect squares that go into 90? Sorting through my perfect squares we looked at a little while ago. You know any perfect squares that go into 90? He says, yes, I do, man. That's 9 times 10. That's the same as 90. I know the square root of 9 is just 3. I don't know the square root of 10. I'll leave it inside that radical. So 3 root 10. Man, that's how long BC is. 3 times the square root of 10 is the length of BC. Let's go find the length of AZ. And what I'm telling you, when we work this out, by virtue of the slopes, the radical that we'll find on the length of AZ will also be the square root of 10. That's kind of a nice thing to know ahead of time. Let's see how that works. See if it comes out that way. I need the coordinates of A, which was at 8, 5, and Z. Z having been at, where do we put our point Z? 6, negative 1. Let's hit it with the distance formula with some care. I tell you, if you just make those marks ahead of time and then Let's go flow through here and lay those things in their places. What goes in the first pair of parentheses, the difference in the x's. Let's go with 8 minus 6. What goes in the second pair of parentheses, the difference in the y's, that'd be 5 minus negative 1. You could write it in the other order. After you square, it's going to be the same. Let's just go. 8 minus 6, that's going to leave me with 2, huh? But I'm going to square it. And 5 minus a negative 1, that's 6. 5 plus 1, that's just 6. But we're going to square that as well. So I got 4 when we square the 2, and 36 when we square that 6. Let's add those radicals, and we got the square root of 40, huh? You might be saying, well, that's 4 times 10. And I say, yes, it is. So let's reduce that radical. That'd be 4 times the square root of, oopsie. I should have written that as the square root of 4 times 10, leaving the 4 and the 10 within the radical. But now I'll think to myself, I do know the square root of 4. It is 2. I do not know the square root of 10. I'll leave it within the radical. So I got 2 root 10. And that beautiful thing happened that we expected to happen. They both have the same radical. You can expect that to happen on an exercise like this I give you. If it happens on a quiz, yes, sir, Bob, that'll happen. The same radical, whatever it might have been. Not always the square root of 10. Now, finish this exercise up. Show the process as you find the area of the triangle formed by points A, B, and C. We're going to figure out how many of these little square units fill in that triangle right there. Remember, area of a triangle is given by 1/2 times the base times the height. Let's find the area of this triangle. I'm sorry, I've hidden from you. 1/2 times, what did you say was the length of that base, mister? And the length of that base is just from B to C. That's our base of our triangle. And BC had length 3 root 10. Times, now we need the height. And AZ is our height. That's the distance from this vertex to this line. Now that's the height of this triangle when we measure it from that base. So let's use the height that we found. And we found the length of AZ to be 2 root 10. Put it in this place, 2 root 10. So we got to multiply these radicals. I don't know much about half of 3 square roots of 10, but maybe we can multiply these guys first. The associative property says we can. Let's just keep that 1/2 for now. Multiply these bears. Outside guy with outside guy gives me a 6. We'll be able to take a half of that in a minute, huh? Square roots of, and 10 times 10 is going to give me 100. Now you might have thought right away, this is the square root of 10 squared, and the square root of 10 squared is going to be 10. Same idea right here. I got a half of 6, that's going to give me 3. And I know the square root of 10, that's going to give me 10. Excuse me, I know the square root of 100 is going to give me 10. So I got 30 out of this, don't I? This becomes 30. It's 3 times the square root of 10. Yeah, that's going to give me 30 units squared. So, I might have made this point a little bigger than it really should have been, but I tell you, there's 30 of those going to